Hello everyone, I'm Alex, thanks for the introduction, and I would actually like to thank the previous speaker because he actually made my life easy in talking about confidence intervals and not enough data measurements. So having said that, I'm going to talk today with you about our work on the reproducibility of performance of big data workloads in modern cloud networks. And this was a large-scale study, and we needed 4 teams to actually work on this. So it was 2 teams in the Netherlands, 2 teams in the US at Santa Cruz in Utah. So thank you guys for your help. Now, for a bit of framing, I'm going to talk today about big data infrastructure in the cloud. And I think most of us actually know that in the previous 10 years or so, there have been much research and development in these topics, so that there's many frameworks, many applications, a lot of infrastructure designed both by industry and academia. And these things run nowadays in the cloud. And for every new service, every new application, every new release, every research paper, or every paper that actually compares any subset of these systems, we need to do performance evaluation. And do we actually know how to do this properly in the cloud? And I think nobody would disagree with me if I'm saying that performance evaluation is difficult anyway in systems in general, because systems are actually quite complex, and most of the time it's difficult for us to understand the underlying conditions of the infrastructure. And I'm going to stress here that clouds do actually exacerbate the performance variability. And because of this, we don't know how many times to perform experiment repetitions, how many data points we actually need to actually summarize our performance. And we don't know exactly what to report. Do we need to report some medians or some simple data points, or do we need confidence intervals? What do we need? And this is difficult, and I want to show you, before getting into more details, some example of performance variability. And in the cloud, this actually happens because of many reasons. So there's all sorts of collocation happening, there's virtualization overheads, there's congestion, noisy neighbors, and so on and so forth. And it actually happens on all types of resources. So CPU, memories, disks, you name it. But in this talk, I'm going to focus on networks. So I have here a figure that is from around 2011. A team at Microsoft Research in Cambridge looked at 8 different clouds. So horizontally in this figure, you can see these 8 different clouds. And what they plotted here is the amount of performance that the users of these clouds could actually see. So vertically in this figure, you could see the amount of bandwidth that VMs in those clouds can actually get. And they are summarized as box plots that range from the 1st percentile to the 99th. And the main takeaway from this figure that I would like to emphasize is that there's a lot of performance variance between clouds, but also within each cloud. And I'm going to stress here that cloud variability actually affects our experiments quite a lot. And in what follows in this talk, I'm going to show you how that happens and why. So first of all, I'm going to show you that variability is actually disregarded quite a lot in performance evaluation studies. I'm going to show you that still, compared to the 2011 study, network performance in clouds is still highly variable. I'm going to show you what that means to actually run applications. And I'm going to introduce some advice to actually get more reproducible experiments, even though we have variability. Now, to begin with, we performed this systematic survey of 4 top systems conferences. I think you recognize NSDI, SOSP, OSDI, supercomputing. We set a time frame of 2010 to 2018. We looked automatically through the PDFs for keywords like, I don't know, big data analytics, data science, and so on. And we got a subset of the entire set of articles. And then through these, we looked manually with a couple of reviewers. And we selected manually the papers that were actually evaluated on clouds. And we ended up with these 44 articles that we found out that they are super important. So they were cited over 11,000 times in May last year. In the meantime, they probably got even more citations, so they got even more important, right? Now, while reading these papers, to actually keep things easy, we actually asked 3 questions. How many experiment runs did the authors run? Did they report some sort of statistical metric? And did they report any kind of experiment variability? And to go into the first question, I have this figure here. Horizontally, we have the number of repetitions, and vertically, the number of articles that did those many repetitions in percentages. And I want to stress here that most of the articles do at most 15, but actually many of them do 3, 5, 9 even, or 10. So I would actually consider that to be quite a few data points. And as the previous author said, we couldn't infer anything significant about the performance that they get only through 3 or 5 repetitions. Now, for the second and third question, we actually found out that only about 50% of the articles reported some form of average or median. The rest didn't actually say what the data points that they plotted were. They could have been max, min, whatever, but we don't know. About 40% of them reported some form of variability through some box plots or error bars or so on. And actually, a lot of the articles were poorly specified. So they didn't say how many repetitions, but they said, for example, this is the median performance that we got. So it's basically very difficult for anybody to actually reproduce that kind of study. So to sum up the findings of our survey, I can say that most of the articles perform very few repetitions. About 50% of them are poorly specified. Again, about 50% of them only report some average or median statistics. Few, about 40%, report variability. And actually, they are very important articles. I'd like to stress that. Yeah, they were cited over 11,000 times. Now, going back to the title of the talk. Is big data performance reproducible in modern cloud networks? Well, thinking at the findings I actually presented earlier, well, spoiler alert, not so much. And to actually show you that, I designed 2 experiments. So the first one, we measured the variability in cloud networks. So we looked at 3 different clouds. We looked at 2 commercial clouds, Amazon EC2 and Google, and 1 private cloud from the Netherlands. And we took some instance types, not all of them, because we didn't have the budget or the time. So what we did was that we took pairs of VMs and measured bandwidth and latency for about a week. And we had multiple types of communication patterns to be able to mimic all sorts of different types of applications. So we have this continuous streaming and then some sort of intermittent communication with a 5-second stream and then a 30-second pause, or a 10-second stream and then a 30-second pause. So based on these kinds of experiments, I want to show you first that in clouds, we get this thing that I call stochastic noise. And there's a problem with that because the cloud performance actually varies between experiments and during experiments. And I have here in this graph about a week of experiments for 3 pairs of VMs, where we measured continuous communication performance and the 2 type of intermittent. So horizontally, there's the time, so about a week, and vertically the performance, mind the gap here. And as I said, performance varies quite a bit between experiments. So the 3 types of experiments have different levels of performance, but it also varies within an experiment. So yeah, we have this deep and performance there, which brings about a 30% slowdown. And to actually mitigate this kind of problem, what we need to do is when we run some applications, together with the application performance result, we might as well plot or present the results of the micro benchmark of the platform, so that people can actually understand what had happened. Now, another source of variability next to the stochastic noise is actually the interference between your experiments and the policies implemented by the provider. So for example, in Amazon EC2, we actually found the token bucket for some of the instances in Amazon. And I'd like to show you here what that token bucket actually means. So when we allocate a VM, we get a budget to actually send or spend at a very high rate, so for example, 10 Gbps. But then after we spend this budget, we are throttled down to a smaller bandwidth. Now, each instance type here, so from the C5 family, so C5 large, X large, and so on, gets a different type of token bucket budget. And I plotted here in this graph vertically the time it actually takes to empty that bucket. And we plotted here with box plots this amount of time. So not only this time is different per VM, it actually increases with the number of cores in the VMs we have, but it also is quite variable itself. Now, as I said before, in this kind of token bucket, we have a high speed and a low speed. And as we can see, the high speed is equal or roughly equal for all the instances. But the low speed actually increases with the number of cores or the number of resources in those VMs. And if you look at this particular case, there's a 10x difference between high and low bandwidth. So you can imagine what happens with your experiment if during your run you would catch the slow speed. And that actually happens. I'm going to show that later. So as a mitigation to this problem, I want to propose the detection, if possible, of behavior that actually breaks assumptions. So if you get suddenly a drop in performance of 10x, that's not stochastic noise. That's something that really happened with the provider. So the main findings of the experiment where we looked at modern cloud networks are the following. So we found and quantified a large amounts of variability that actually depends on the access pattern. It's quite different between providers. And we found two types of variability that there could be more. So the first one is stochastic noise, and the second one is given by provider quality of service policies. Now, to see what actually this means for big data experiments, I designed the second experiment. So we ran HighBench and TPCDS on Apache Spark. And to see what happens between applications and stochastic noise, we ran directly on the Google Compute Engine. And to see what happens with quality of service policies like token buckets, we actually emulated the Amazon token bucket on our own infrastructure to actually be sure that we cut down all possible stochastic noise. Now, I promised you that I'm going to talk about confidence intervals, so here I am. So I'm going to show you now what stochastic interference brings to your experiments. So in this figure here, I'm showing the number of repetitions of the same experiment horizontally, and vertically the performance in seconds, if you will. So with this thick blue line in the middle there, I'm plotting the median performance. With the shaded blue area, the lighter blue area, we have the 95% confidence intervals for the median. And with this dotted red lines, we have this error tolerance for the confidence of the median. So what we want is that these confidence intervals are narrow enough to actually fit into these errors that we establish beforehand. So as the previous speaker said, we want to have narrow enough confidence intervals so that we're actually sure, or as sure as possible, that our result is meaningful. So let me stress that first, that usually articles run 10 to 15 repetitions if we're lucky. So we're here with very low confidence. And as the number of experiments increase, we get to much better confidence, and we can be sure that the median per performance is, well, somewhere there, and we're 95% sure that it's in that confidence interval. Now, having said that, the mitigation to this kind of problem is to actually run many experiments, go way beyond people actually do. Well, now, having said that, I'm going to show you an even more interesting problem. So I just said you should run as many experiments as possible. Well, if you do that on the token bucket, yes, it actually happens that the token bucket breaks assumptions. So you're assuming that when you're running some experiments, your probes are from the same distribution and are independent. But if you're running experiments repeatedly on a token bucket, you're depleting the token bucket, so experiments are no more independent. And the distribution actually changes when you deplete the token bucket and you get a different level of performance. So horizontally here, I have, again, the number of measurements. And vertically, I have time. The same color coding there. The thick blue line is the median performance. Then we have the confidence intervals. But I also plotted with those shades of gray the budget in the token bucket. And while we decrease that, we see that the performance drops. The confidence intervals widen. So that's not good. And that basically means that the performance we get out of this experiment is not meaningful at all. So the mitigation to this kind of problem is to actually, if you can, randomize experiment order, do not reuse the machines or you reuse them sparingly, try different days, try to rest the infrastructure to get your token bucket increased again, and so on. Now, I would like to stress that this kind of behavior is not, cherry-picked by us. So about 80% of the TPCDS queries that we ran with the token bucket have the same kind of behavior. The rest 20% are not very network bound, so for them it didn't matter. Now to conclude, the main takeaway from my talk, if you want, please run more experiments. Okay, getting more serious. I think I actually convinced you that network performance variability is quite widespread, and the systems community actually neglects this phenomenon when running experiments in practice. And this introduces quite an important reproducibility problem. So as I said before, we need to run more experiments to be sure that our research is reproducible. We were the first to quantify these kinds of things, but I think it would take a community effort to actually solve it. So I was thinking of organizing a Dagstuhl seminar on the reproducibility of performance for systems. And if you're interested in joining, please just talk to me or my colleagues in the breaks. Thank you.
Questions. So I do think that one of the problems that we need is like more flexible deadlines, because close to the deadline you don't have time to run as many experiments usually. I think everybody has been there. But I have a question for you about the token bucket that you were talking in Amazon. So is it something that you want to remove, or you want to make sure you're hitting that? Because depending on the application, you might actually, in the real scenario, have that limitation. No?
Yeah, you might have that limitation. So I don't know if we want to remove that. So probably the provider, for some good reason, introduced it. What we want in practice, especially when we run experiments that we need to be sure of, is to actually try multiple times. Try to see if there's a token bucket, first of all. Try to see what happens if we deplete it. And if nothing happens, perfect. If something does happen, I don't know. Maybe we present two levels of performance, with the token bucket and without.
Okay. You have a quick question?
Thank you. Thank you very much for the talk, Marius from EBFL. So I have a question specifically about this token bucket issue. Whenever people describe their experiments, they state some specific assumptions. For example, they might assume that you have a specific interarrival distribution that comes from a distribution they can formally describe. And in this case, with this token bucket behavior, you don't respect this distribution.
Not at all.
So I think my comment here is that the problem is that you don't run the experiment in the way you think you are running it, as opposed to...
Correct.
Okay. So do you have a comment on that, or do you think that the actual platform should be considered part of the experiment?
Yeah, that's actually a great point. So definitely the platform is part of the experiment. So that's why I think at some point I said you need to document as much as possible the behavior of the platform, right? So try to micro-benchmark it beforehand, try to understand a bit what it does. Then you should go to the real experiments and see if the results that you got through those micro-benchmarks make any sense when you run the real application. And if they don't, go into more depth and see what the interaction is. Maybe you find that token bucket like we did, because we found it just by trying a lot of experiments. We didn't know it existed actually. So yeah, I think the real issue is to actually try to understand the platform as well as possible and publish as many performance results and micro benchmark as possible when you publish your performance results for your system.
Okay, let's thank the speaker again.